Hello friends, I am Dr. Himani Garg, working as professor in Department of Electronics and Communication Engineering in AKGEC Engineering College. And today I am going to discuss about improving coverage and capacity in cellular system. And my slides will include introduction, cell splitting and cell sectoring. Now, firstly coming to the introduction part, as the number of users increases, the number of channels assigned to a cell becomes insufficient to support large number of users. As we know that the bandwidth is limited, so we have to use the concept of frequency reuse so as to provide services to more number of users. Therefore, cellular design techniques are required for improving coverage and capacity. So, we have to design different techniques for increasing the capacity of the system, and the techniques that are used for increasing the capacity are cell splitting, cell sectoring and microcell zone concept. In this lecture, we will be discussing about cell splitting and cell sectoring. These two techniques we will be discussing about. So, firstly we will start with cell splitting. As you are aware from the name itself, cell splitting means we are splitting the cells. Now, if you consider this as a cluster of 7 cells, that is, these are called macro cells. These bigger cells are called macro cells. These smaller cells are called micro cells, and these smaller cells are called micro cells. So, this technique of dividing a macro cell into micro cell or picocell depending upon the number of users is called cell splitting. Now, in this cell splitting process is used in the congested areas where the number of channels required are more. Now, this cell will be having smaller cells, these will be of smaller cells, and each with its own base station and a corresponding reduction in antenna height and transmitter power. Obviously, when the size of the cell is small, then the antenna that will be used here, the base antenna that will be used here, it will have to cover smaller area, so its transmitted power will be less as well as its height will be less. Now, why we are doing this? Because it will increase the capacity due to additional number of channels per unit coverage area. The number of channels per unit coverage area will increase because these cells that we will be using, we were using the concept of frequency reuse. Now, that frequency can be reused within this particular area also. Now, it also increases the number of times channels are reused. So, we can say that cell splitting increases the number of, can provide services to more number of users. Now, we will see this with the help of example. Now, in this diagram, you can see this is the larger cell that is used for low density, so as to provide services to low density. This is smaller cell. Now, we have decreased the area of the radius of the cell by r by 2. Earlier, the radius is r. Now, the radius is r by 2. This is macro cell. This is micro cell. This is micro cell, and the smaller one, this is, if the area we are taking as R4, this is picocell. Here we are considering the different areas, and on the basis of, these are on the basis of density of users. Now, I am taking the example here. Cell splitting can be done by reducing the cell from radius from r to r by 2 or r by 4. If the radius of the new cell, smaller cell, is r by 2, now area of older bigger cell, that is denoted by A naught, that means O here suggests the older cell, area of older cell. As the radius of the older cell was r, so its area will be pi or r square. Now, the area of newer smaller cell, that will be denoted by A of n, and as the radius has reduced from r to r by 2, so its area will be A pi into r by 2 square, and that will be equal to pi r square by 4. As it is clear from equation number 1 that now 4 new areas will be equal to 1 older area. 4 new areas will be equal to 1 older area of, or the area of the newer cell is 1/4 of the older cell. So area of the newer cell is 1/4 of the older cell. Now in order to cover the entire surface area with small cells, approximately 4 times as many cells are required. Therefore, the capacity of the system increases by 4 times, because the capacity depends upon the coverage area, how we are reusing the channels within the particular area. So if you are decreasing the radius by r/2, then the frequency reuse increases by 4 times. The next slide we will see how it is done with the help of example. Now, before cell splitting, if you consider the case that the bandwidth is 25 megahertz, total bandwidth allotted is 25 megahertz, and each user is using 25 kilohertz. Total bandwidth available is 25 megahertz and each user is using 25 kilohertz. Then the total number of users that this antenna can serve is 25 megahertz divided by 25 kilohertz, that is equal to 1000 users. So the number of users in the older area is 1000. Now we are talking about, now this thing also, as older area is 4 times the newer area. Now 4 newer area is equal to 1 older area. So for 1 older area, new area, we can serve 1000 users, as 4 new areas will be serving 1000 into 4, that will be equal to 4000 users. So this is clear. It is clear from this example that capacity of the system has increased by 4 times with the help of cell splitting, and our aim was the same, that we should provide more number of users, more number of channels should be provided for a particular region. Now this is possible with the help of cell splitting. Now another condition is also there, cell splitting also decreases the power emitted by a transmitter. Now we will see how, with the help of this example, that how it is affecting the power. Reduction in transmission power with the help of cell splitting. Let us take PT1 is a transmit power at old cell boundaries and power required at old cell boundary as PR1. Now we are considering the another case where we are considering the PT2 as the transmit power at new cell boundaries. New cell boundaries are the boundaries where we had taken the radius as r/2, and earlier we had taken the radius as r. Clear? So now if PR2 is the power required at new cell boundaries, and whenever we are talking about power, then we have to consider a parameter alpha, that is called path loss component. And when we calculate the power received, it is given as power received is equal to power transmitted into r to raised to power minus alpha. This is for the older cell where we have not used cell splitting. Now in the second thing, we are using the cell splitting approach, in which we have reduced the radius by half. So the new radius is r/2. Now we will see what is the power received in the case of radius r/2 in the cell where the radius is half of the older one. So the power received in the new cell, that is equal to power transmitted by the new, and radius here is r/2 raised to power minus alpha. Now you have to consider this thing, that we are not changing anything else than the radius. Nothing else is being changed. So the frequency reuse plan will remain the same. As the frequency reuse plan will exactly the same, for the new cells they will behave in the same manner as the earlier one. So PR1 is equal to PR2. So PR1, as frequency reuse plan is the same, PR1 is equal to P12. In this case, we will be equating the equations third and fourth. If you equate both the equations, third and fourth, then ultimately if you take the log both sides, and one thing more, we have to consider the value of alpha as 4. We are taking an example where we are considering the value of alpha as 4. Now you can see power PT1 by PT2 is equal to 12 dB. After taking the log in this equation, we have got the value of power transmitted T1 upon PT2 is equal to 12 dB. That means transmitted power is reduced by 12 dB with the newer cell. As earlier, the base station has to cover more area. Now the base station, in the case of macro cell, the area was more, the base station had to cover more area, so it had more to transmit more power. But in the case of microcell, the area has decreased, so it has to cover smaller area. Then this one, the area of both is less. You compare, you can this one is lesser than the earlier cell, so that's why the power is reduced by 12 dB. So 12 dB power is reduced. So with the help of cell splitting, we can increase the number of users, as well as by using smaller antennas, we can increase the coverage area, as well as the power that is transmitted will be reduced. Now the limitations. We are using cell splitting, but it has its own limitations. We will see that as we have divided the cell into smaller areas, and each cell will be using different frequency. Each cell will be using, now this each microcell will be using different frequency. As different frequency is being used, so one user, if it is moving, is mobile and it is moving from one cell to another cell. I am talking about the microcell. If it is moving from one cell to microcell to another microcell, then handoff should occur, because one microcell is working on a particular range of frequencies, another microcell is working on, adjacent microcell is working on another range of frequencies. So one user is moving from one cell to another cell, then there should be handoff. As the number of cells are increased, so the number of hops will increase, so it will put a burden on the MSC. So this is one of the disadvantages of the system. The channel assignment becomes difficult, because at every as the mobile is moving from one cell to another cell has to provide the channel to that particular user. Then it becomes difficult to provide the channel. All cells are not split simultaneously. Now the cell splitting approach is not done for all the cells. It is done according to the congestion. If any particular area has more congestion, then that area will be divided into cells. Another cells will not be that will be divided into microcells, but other areas will not be divided into microcells. So in that way, there will be, the cells are not split simultaneously. So special care have to be taken for proper allocation of frequency. So it becomes difficult to supply so as to provide allocation of different frequencies on the basis of microcells. Now, the second approach that is used for improving the coverage and capacity is cell sectoring. Now, this cell sectoring is totally different from the concept of cell splitting. In cell splitting, we were using frequency reuse, and we were also providing more number of frequencies per unit coverage area. But this concept is totally different. Now, there is the term called signal to noise ratio or co-channel interference. Now, what we mean by co-channel interference? If two cells are using the same set of channels, then there will be interference between them. That is called co-channel interference. Now, if we will decrease the co-channel interference and increase the signal to noise ratio, that means signal level is more and the noise is less, then the number of users can increase. So cell splitting works on this technique. And what we are doing here, in the earlier case, when there is no cell splitting, then we are using one omnidirectional antenna at the center of the base station. But with the cell sectoring approach, we are using unidirectional antennas that will be pointing in a particular direction. As you can see, other technique to increase the subscriber capacity of cellular network is to replace the omnidirectional antenna at each base station by 3 sector antennas that are 120 degree or 60 degree opening. That can be 120 degree or 60 degree opening. Now, this technique decreases the co-channel interference. As I have already told you, that this method depends upon is dependent upon increasing the signal to noise ratio and decreasing the co-channel interference. Thus, increases the system performance by using directional antennas. Clear? Each sector can be considered as a new cell. So, you can say in which direction a particular antenna is propagating, that will be considered as a particular cell, because that antenna will be directed towards a particular area and that will be using a particular range of frequencies. So, it can be considered as a particular cell for this particular area. Each sector can be considered as a new cell with its own set of frequency channels. The base station can either be located at the center of the original large cell or the corners of the original large cell. So, as you can see here, the base station can be at the center. Now, if we are using the base station at the center, then at the center base station there will be another directional antennas that will be mounted on this particular base station. There will be sectored or directional antennas that will be mounted on this base station. Now, the positioning of these antennas can be, first one is omnidirectional, that is without sectoring, but the sectoring can be 180 degree, 120 degree. As you can see, this is 120 degree sectored cell, and this is the alternate arrangement for 120 degree cell. This is 90 degree sectored cell, another is 60 degree sectored cell. So, if you are applying the antennas to this particular cell at this particular sector, then they will be directed to that particular cell and they will be working on a particular range of frequencies. Now, antenna change from in cell sectoring, we can see here the antenna has been changed from omnidirectional to sectored. Now, if you take the example of this antenna number 1, it will be directed towards this particular sector 1. It will be propagating, it will be covering this particular area. This sector will be, sector number 2 will be covered by this antenna. This sector 3 will be covered by this antenna. So, you can say here we are using frequency F1, this is F2, this is F3. So, all these sectors will be having different range of frequencies. Antennas are not placed near to each other, otherwise there will be adjacent channel interference will be there. There is another concept also, adjacent channel interference. So, when we are placing the antennas, that the care should be taken that these antennas are not close to each other, otherwise they will cause interference, that is adjacent channel interference. They are not working, they are not co-channels, they are not working on the same frequencies, they are working on different frequencies, that's why they are called adjacent, and there will be also disturbance due to this adjacent channels. Sectoring increases the signal to interference ratio by using directional antenna so that cluster size may be reduced. Cluster size has been reduced. Sectorization is less expensive than cell splitting as it doesn't require the acquisition of new base station sites. As we had seen in the earlier slides, that cell splitting is dividing the cells into smaller cell, and each cell is having its own base station. Each cell is having its own base station, so that will increase the cost of the system. But in this case, we are using only antennas that are sectored for a particular direction, and that is for a particular area of the cell. Now, we will see in this diagram, you can see that how the co-channel interference has reduced with the use of sectored antennas. Now, this is an example. Here we have used a cluster of 7 cells. There is a cluster of 7 cells, and you can see that this center one is using 5 number, shows that this particular cell is using a particular range of frequencies, and we have given it number as 5. Now, this cluster, this another cluster is there. There is another cluster. There is another cluster here. There is another cluster here. There is another cluster here, and this one also. Now, 5 is written here, 5 here, 5 here, 5, 5, 5. So, this 5 also. So, that means these all cells are using the same channels. 5 number here, 5, 5, 5. Note that these all cells are using the same set of channels. That means these are also called co-channels. Co-channels. If these are co-channels, that means they will ultimately lead to co-channel interference if we are using omnidirectional antenna. If omnidirectional antenna has been there, then this particular cell at the center will get interference from all these 6 cells because they are working at the same co-channel frequency, and that's why they will be affecting the signal here and will decrease the signal to interference ratio. So, the level of signal will decrease due to interference from all these co-channels. Now, this is the case without sectored antennas. Now we will consider the case when we have used sectored antenna. As you can see here, if we are using sectored antenna at this place, at all these places, if you are using sectored antennas, this shows sectored antenna that is directing its signal to a particular direction. This is the direction of the antenna. This antenna is also directed towards this direction. This antenna is directed towards this antenna. This is the direction of propagation, direction, this is the direction. So, as you can see, it is clearly visible that this center cell is getting interference only from this cell, co-channel cell, as well as this co-channel cells. These cells not affecting the signal at the center. So, the number of channels, that co-channels, have been reduced to 2 from 6. Earlier 6 co-channels were interfering, now only 2 co-channels are interfering. If the co-channel interference has reduced, then signal to noise ratio will increase and we can provide services to more number of users. So, this is the concept of cell sectoring. Now, there are limitations for cell sectoring also. In the case of cell splitting, we will have to use more number of base station, whereas in this case, the number of antennas have increased at each base station. There is a loss of traffic also. Since sectoring reduces the coverage area of a particular group of channels, the number of handoff increases as well. As you can see here, the area covered by a particular antenna is now less, so the handoff will also increase. In this case also, load on the MSC is also increased in this case. So, these are the references, and thank you for watching this video.